In this video, we will look at 15 essential best practices for FastAPI. These are tips every FastAPI developer should know, covering everything from async rules and database connections to logging, background tasks, and even deployments. By following these, you will be able to avoid common mistakes and build applications that are both high performing and truly production ready. Number 1. Never use async def for blocking operations. In Python, blocking operations are tasks that make your program wait until they are finished before moving on. For example, time.sleep will pause your program for 10 seconds. Other common examples include reading from or writing to files, making HTTP requests with libraries like requests, or performing database queries using synchronous clients such as Mongo client from PyMongo. Now here's the crucial part. FastAPI runs endpoint functions defined with async def in the main thread. If you put these blocking operations inside an async def function, your application will become unresponsive. It won't be able to process other requests until that blocking operation finishes. The solution is simple. Define these functions using a regular def keyword instead of async def. FastAPI is designed to recognize that you are performing blocking operation within these def endpoints, and it will intelligently run them in separate threads. This way, your FastAPI application remains responsive. Number 2, use async-friendly code. To get the most performance out of your FastAPI application, use non-blocking libraries as much as possible. So you can declare your endpoints as async endpoints. Use asyncio.sleep instead of time.sleep, HTTPX async client instead of the request module, and motor instead of PyMongo. I hope you get the idea. Number 3, don't do heavy computation in FastAPI endpoints or you will block your server. FastAPI is designed for I/O bound workloads, so avoid processing images or videos or running heavy machine learning models directly in your endpoint. The reason is that your application will be unresponsive for as long as the computation runs. What should you do instead? If your ML model is lightweight and inference is fast, say under 100 milliseconds with low traffic, or if you are just prototyping, you can get away with using FastAPI directly. But for heavier ML models, use dedicated inference engines like Triton, TensorFlow Serving, or TorchServe, and then use FastAPI to validate inputs and route the request. For truly long-running computation, use a queue plus worker system. When client sends a request to FastAPI, FastAPI enqueues a job to a message broker like RabbitMQ. A separate worker, example salary, pulls the job from the queue, runs the heavy computation on CPU or GPU nodes, and stores the result in a database. By the way, if your FastAPI app is slow, you'd like me to take a load, just send me an email here. Number 4, the previous rules for endpoints also applies to FastAPI dependencies. Define your dependency with def if you are doing any blocking operation inside. Use async def if it's lightweight, CPU bound, and entirely non-blocking, and don't perform any heavy computation inside your dependency. Number 5, don't make your users wait. When you have operations that don't need to block the client from getting a response, things like sending a confirmation email or logging event, you should avoid making the client wait by doing it in the endpoint. Instead, use FastAPI built-in background tasks. They are perfect for small, non-critical fire and forget tasks. Since these background tasks run within the same event loop as your main application, you will want to follow the same rules for deciding between async def and def when defining them. However, it's crucial to understand the limitation. Don't use background tasks for anything requiring guaranteed delivery, retries, or tasks that run for a long duration. For those more robust needs, a dedicated message queue and worker system like salaries is still the superior choice. Remember, if your FastAPI process crashes before a background task completes, that task will fail. Number 6, don't expose FastAPI Swagger or ReDoc in production unless your API is public facing. FastAPI automatically generate these docs, which is great during development, but in production, they can reveal endpoints that might still be incomplete or lack proper security. To prevent this, make sure to set docs URL, redoc URL, and open API URL to none in your production settings. Create a custom base model and use it to define your Pydantic models. The benefit is that it's easier to manage your global configuration in one place. For example, if you want to return camel case to the front end but prefer snack case in Python, you can set an alias generator to handle that. Another common use case is simplifying JSON encoding when returning data. If you try to return a date time or decimal object, you will get an encoding error. So define your encoders globally. You can format datetime object as strings, convert decimal to float, and if you are working with MongoDB, convert object ID instances to strings. Number 8, don't manually construct a response model in your FastAPI endpoints. If you have set a response model, there's no performance benefit to creating that model yourself just to return it. FastAPI will do it anyway. It first converts your return value to a dictionary or a list, validates it against the response model, and then encodes it to JSON. Just return a plain dictionary and let FastAPI take care of the rest. Number 9, validate with Pydantic and not your code. Push as much validation and structure definition as possible into your Pydantic model. That's what they are built for. Don't scatter validation across your route function with if statements and manual checks. It might seem easier at first, but it quickly turns into a mess. You lose consistent error responses, and clients get cryptic for hundreds with no clue why their request failed. You end up repeating the same logic in multiple places, and the worst part, your OpenAPI docs won't reflect any of that hidden validation. If Pydantic doesn't support the validation unit, don't write it inside the endpoint function. Add custom validation logic directly inside the model instead. Number 10, use dependencies for DB-based validation. If your validation logic requires a database query, like checking whether a resource belongs to the current user before allowing changes, don't put that logic directly in your endpoint. Instead, create a dependency and use it. The first benefit is that you can easily reuse the dependency across multiple endpoints with just a single line of code, and there's no performance hit. Since FastAPI caches dependencies per request, your dependency will be evaluated only once in a request. Overall, it's efficient and helps keep your endpoint clean. Number 11, avoid creating a new database connection in every endpoint. Instead, you should use a connection pool and access these connections through dependency injection. There are two common ways to do this. The first one is storing the DB connections pools in the app state. You initialize the connection pool within the lifespan function and then store it in app state. After that, you create a dependency that retrieves a connection from this pool. You will typically use an async with block to ensure the connection is properly released. This method makes it straightforward to clean up resources during shutdown, which is particularly helpful if you are working with multiple databases. Second, the legacy global style pool. This approach involves defining the connection pool as a global variable and populating it during the app's lifespan event. While the first method, storing in app state, is recommended approach, you will still frequently encounter the global style pool in many existing code bases. Number 12. Use the new lifespan event for managing app level resources. It's better to use FastAPI newer lifespan feature instead of the older app on event startup and app on event shutdown decorators. Lifespan gives you a single unified context to handle setup like initializing database connections, cache clients, or starting background tasks, and clean up when the app shuts down. It keeps your startup and shutdown logic together, which makes things easier to manage and reduces the chance you will forget to clean something up. And if startup fails, lifespan still ensures cleanup happens, which isn't guaranteed with the old way. Number 13, don't hardcode secrets in your code. Use env files and config classes to access them. Never hardcode values like passwords, API keys, tokens, etc. directly in your source code. Instead, use a .env file and make sure to add .env to your .gitignore so it doesn't end up in version control. It's a good idea to include a .env.example file in your repo. This acts as a template showing what environment variables are expected without exposing any real secrets. Keep it up to date. It should closely mirror the actual .env structure. That said, try not to overload your .env file with things that control business logic or complex behavior. Keep it focused on static configuration. Stuff like port numbers, DB URLs, credentials, and simple toggles like debug equals true. Anything more dynamic is usually better off handled directly in code. Also, avoid accessing os.environ all over your code base. It gets messy fast. A better approach is to centralize everything in a config class, something like a settings class. In my project, I use Pydantic's base settings. It validates all your environment variables upfront. If something missing or misconfigured, it fails early right when the server starts, and it makes switching between development and production environment a lot smoother. Another solid option is DynoConf. It's more flexible and support things like multiple environments and layered settings. Number 14, use structured logging and avoid relying on simple print statements for logging. The print function simply doesn't offer the control and flexibility we need. For instance, there is no built-in way to specify a log level or automatically add context like request ID, timestamps, Debugging with print can quickly become a nightmare because you can't easily filter out irrelevant messages. Every print statement has the same visibility. Instead, I highly recommend using Python, the standard logging module, often paired with powerful libraries like Logguru or structlog. These libraries allow you to assign a criticality to your logs, whether it's something for debugging, an informational message, a warning, an error, or a critical alert. This becomes incredibly useful when you are running your application. Depending on the environment, whether it's development or production, you can set the log level. For example, you might set it to debug or info or error, which gives you fine-grained control over what messages you see. In development, you will likely want to see everything, so setting the log level to debug is common. However, in production, you will probably want to set the log level higher, perhaps to info or error, based on your specific operational needs. Another incredibly useful practice is to add contextual information to each log, such as request ID. Unlike print statements where you have to manually add this to every single one, libraries like structlog allow you to create a middleware that stores context variables. These context variables safely pass request specific data across synchronous calls. Then within your logger configuration, you can configure it to include the context variables, time, log level, and the actual message. The request ID is just a simple example. You might also want to log other contextual information like the user ID. Just make sure you are never logging anything sensitive like database credentials or API keys. Finally, if you are running multiple instances of your application, it's a good practice to centralize your logs. To do this, you will likely want to push these JSON logs using FileB to Elasticsearch for centralized storage and analysis. And for our last point, number 15, we are talking about the best practices for deploying FastAPI. For local development, UVCon on its own is perfectly fine. However, when you move to a production environment, you should run UVCon with Gunicon, specifically using the UVCon worker class. Next, make sure to install UV loop in your Python virtual environment. FastAPI will automatically detect and use UV loop instead of the default Async IO event loop, which can provide a significant performance boost. Finally, you will want to tune the number of workers to match your server's CPU. A common starting point is to set worker equal to CPU cores times 2 plus 1. However, this isn't a hard and fast rule. You should experiment and benchmark to find the optimal number that maximizes your server performance. If you are looking to scale your application further, consider containerizing it using Docker. Don't forget to drop me an email here if you want me to review your application.